Hello. So we talked about frequency response last time, and this time we're going to generalize this whole concept of frequency response into what we call the discrete-time Fourier transform. So the frequency response we found was defined as the sum over the impulse response multiplied by this complex exponential function. Now, the discrete time Fourier transform, that's a mouthful, so we just say the DTFT, is defined in the same way, actually. The only difference being in how it's interpreted. So in this case, we are summing over, in this case I put a x in there to show that it could be a signal, and doing the same operation we did before. Now, one thing that's common is to change this around, so we're summing over, and it's just really a change in variable. It's not a change in anything discrete, but it shows us, it illustrates that we're starting with a time domain signal and we're converting it to what we call the frequency domain. So x e to the j omega is a function of now omega, so it's continuous in frequency. And we already saw, and we know that x of n is discrete in time, in as much as n is time. Now, how do we go back? Once we've done found our frequency response, if you will, or our DTFT of a signal x, how do we go back and get the time signal? Well, there are two ways really. The first is by this equation. So far we've developed everything kind of from first principles, and now I'm just throwing this at you and telling you that that's the way the world is. We'll go through a demonstration and show that this is the case. Where we come up from this is actually, as we've been talking about linear algebra concepts of, say, eigenvalues and eigenvectors, this comes from a vector space concept of orthogonality. And so there are other ways of getting to it. But why don't we, I guess, just actually, let's go into the properties first. We can go into a demonstration of this later or in some ancillary materials. So, the discrete time Fourier transform, and therefore frequency responses, which are simply a DTFT of the impulse response, have a variety of properties. These are listed in the textbook. I just wanted to highlight a few. If we conjugate x, then we conjugate its DTFT, and we negate the frequency values. So what does this mean? Well, one thing to note is that since, or rather if x is real, then x e j omega is equal to x star e to the negative j omega. In other words, we have conjugate symmetry, meaning that if you were to take x of e to the j omega and flip it on the omega axis and then conjugate it, it would look the same as it did before. So we actually take advantage of that quite a bit. I have a graduate student that used that property, told me about just the other day, to avoid having to compute half of a quantity, knowing that it was conjugate symmetric, saving a lot of computation time and thereby just beating out the fastest published method of doing a particular type of problem. So that's useful. We have conjugate symmetry going the other way. Now this kind of happens all over the place. We get these symmetries. In other words, if there's something that we do in time resulting in something else happening in frequency, if we reverse that and perform the same operation in frequency, then the operation corresponding in time is usually about the same. So here we conjugate and negate in time, and we conjugate in frequency. Whereas above, if we conjugate and negate in frequency, we conjugate in time. So we get these nice symmetries. If we take the real part of x of n, then that gives us the functional even part of its DTFT. So there are a variety of things that are just variations on that theme, but let's go through how we would actually do this. It's not too hard, and it will help you to see how you might get any of the others. So if I had x star of n, and I'm going to compute the DTFT using the DTFT formula, I would really like to get this in terms of the DTFT formula as a function of just x, because I have that defined already as the DTFT of x. So what can we do? We can conjugate the whole thing and that gets us partway there. Now it's looking a lot more like the DTFT of x, except that the sign in the exponent is wrong. Well, if we go ahead and now change the sign on omega, we're where we want to be. We have the DTFT of x with a negative omega, and the whole thing is conjugated. So that's where we get that. I'll go over some more properties and examples in the next lecture. Thank you.